All right, so here we are, last lecture before your exam. I'll talk about the exam a little bit at the end of this lecture. I usually like to try to keep the lectures before a big exam short, to give you the students time to kind of catch up on any material that maybe you've fallen behind on, to kind of tie up any loose ends. Typically, what I would do is have a longer than normal lab, right, which gives some opportunities for some extra one-on-one time. So in this instance, I guess kind of the closest equivalent to that that I could pull off is probably do some extended office hours this week to kind of make sure that all of you are in kind of the best possible position to succeed, right, moving into your exam next week. So just kind of a little bit of wrap-up material. Nothing too heavy, but still important and certainly fair game for next week's exam. So so this chapter is all about correlation. So let's kind of think back to kind of our earlier discussion of correlation. I guess kind of back to week one of this class. So remember, in this context, right, for a single predictor X, right, we've always thought of correlation as a relationship between two variables, X and Y, right? Correlation measures this idea of a bivariate relationship. Works great when we were talking about simple linear regression, but requires a little bit more creative thinking now that we've moved into a multivariate framework. And then that's kind of what this whole week's going to be about. But before we get there, let's review, right, the sort of bivariate correlation. First off, right, R, the sample correlation coefficient, is an estimate for the Greek letter rho, right, which symbolizes, right, a population parameter. It symbolizes the population correlation. Both R and rho range from -1 to 1. R squared measures the strength of a linear relationship between X and Y. In fact, right, we could show mathematically it's SSR over SSY. And so that means that it's the proportion or percent of the overall variability in Y explained by its straight line relationship with X. I'm actually not sure that I showed us this particular equation. And it is an interesting one, right? We can see that the correlation is related to the slope by this kind of factor that is determined by the standard deviation of X and the standard deviation of Y. And so notice, based on this equation, if either one of those are 0, it implies the other one is 0, right? If the slope is 0, then that means the correlation's 0. If the correlation's 0, right, assuming we have non-zero standard deviations, then that means that the slope had to be 0. Right? Which implies what? It implies that a hypothesis test for whether or not the slope is 0 is equivalent to a hypothesis test of whether or not the correlation is equal to 0, right? That was kind of one of the big takeaways. It gives us sort of two different ways to conceptualize the broader, more general idea of a relationship between X and Y. We can think of a relationship between X and Y as meaning it has a non-zero correlation. We could also think of it as meaning it has a non-zero slope. And testing either one of those is equivalent. We're testing the same kind of underlying concept or idea. So that was the bivariate framework, but the last couple weeks we've moved into this multivariate framework. Most recently, we learned how to do, right, 3 particular tests. Right, so what we just observed in the bivariate simple linear regression framework, we saw that a test for the significance of slope is equivalent to the test of the significance of this bivariate correlation. Now we have 3 new, more general tests. One is the overall F-test. The second is the partial F-test. and the third is the chunkwise f-test. What we are going to do this week, what this chapter from our textbook does, is it shows us, it showcases that each of these three tests has a sort of correlation equivalent. In particular, we're going to talk about 4 types of correlation. One is called zero order correlation. That's like the correlation we talked about in week 1. Then we're going to talk about multiple correlation. That's the correlation that corresponds to the overall f-test. We're going to talk about partial correlation. That's the correlation that corresponds to the partial f-test. And then we're going to talk about multiple partial correlation. That's the correlation that corresponds to the chunkwise test. Yeah, so here's zero order correlation. It's just the usual 2-variable correlation discussed in chapter 6. We know that for any k variables, we can make a k by k matrix of zero order correlations by using proccore in SAS. All right, so here's back to our much ballyhooed Bayer data set. We can use proccore. We can put any number of variables in that var statement. And then here's the correlation matrix that comes out, right? So the correlation between length and neck, for example, is 0.87227, strong positive linear relationship between the two. And then the number underneath that, the less than 0.0001, that's the p-value. It's indicating that that correlation is significantly different than 0. Right? So if we were to fit a simple linear regression model between length and neck, the variable, the test of slope would be significant as well. Now, let's focus on our y variable, which is weight. And this will be useful for us kind of later in this discussion or later in this lecture. Which variable is most highly correlated with weight? So weight would be our y variable. We have, in this case, 4 potential x variables. Of the 4 potential x variables, length, neck, chest, and age, which one is most highly correlated with weight? Exactly, it's chest, right? Chest has a correlation of a 0 order correlation of 0.96238. So imagine that type 1 model building approach that we talked about last week. We said you put the best variable in first, and then the next best variable, the one that adds the most above and beyond the variable that's already in your model. So in this example, our best variable, if we were to do a type 1 approach, the variable we would add first to our model would be chest. Now, that's 0 order correlation. Let's now talk about this idea of the multiple correlation coefficient. So this is denoted by capital R with a subscript y given, right? A bunch of x's. Those x's are independent variables. It estimates some population parameter rho, and it basically is a measurement of the strength of the relationship of the observed value of y to the predicted value of y hat, using all of our x variables, right? So the multiple correlation coefficient actually is essentially a bivariate correlation, a 0 order correlation. It's just a bivariate correlation between y and y hat. And of course, that y hat is generated using all of our x's. So all of the variables come into play one way or another. We use all of those x's to generate some variable y hat, and then we look at the relationship between y and y hat. It turns out that this is also the positive square root of r squared, right? So we talked about r squared. That's the SSR over SSY. It's the positive square root of that thing. Does that make sense that the correlation will always be positive? That's kind of what we're saying, right? And in theory, it's possible for there to be negative correlations, but what we're basically saying is in this context, it will always be positive. Does that make sense? It should, right? Because, I mean, the y hats are supposed to be our best possible guesses for y. So we would expect them to have a positive, not a negative relationship, right? That is, if the actual value of y is large, we would expect our best guess to also be large. If the actual value for y is small, we would expect our best guess to be small. So the fact that we're comparing y to y hat, and that y hat is essentially the best possible guess that could be generated for the given x variables in our model, implies that this has to be a non-negative correlation. And so consequently, we could always find this thing in one of two ways. We could actually just do proc core on y versus y hat. We could also just take the r squared, which is part of our proc reg output, and just take the positive square root of it. Okay. So r squared is an estimate of this thing called rho squared. That rho squared has these different variance components in it. That actually, if you look at it, what does that really look like? That's really just like the population analog of SSY minus SSE over SSY. Right? And that's what r squared is, right? R squared is SSY minus SSE over SSY. Rho squared is just this kind of actual sigma squared y minus that sigma squared error. That's what MSE is estimating over the variance of y. And it turns out that the overall f-test that we do through that ANOVA table is equivalent to testing whether or not this correlation is zero or non-zero. So just like before, right, we have this equivalence. Sometimes it's convenient to think of the overall f-test testing, right, whether or not all the slope coefficients are zero. Sometimes it's convenient to think of this thing in terms of r squared, right? Is this r squared significantly different than zero? It turns out that both of those tests are testing the same thing. They ultimately have the same test statistic and ultimately will have the same p-value. And of course, since they have the same p-value, they're going to lead to the same conclusion. Okay. So let's look at the bears example. All right, here we can see our r squared. Where is it? I see you. Our r squared is 0.9427. So the actual overall correlation coefficient will just be the square root, the positive square root of 0.9427. Which is, according to Google, 0.971. Easy enough, right? More generally, right, it's a nice way to kind of think of something in two different ways, but this way of thinking about r squared is going to be more powerful down the road. So why do we care about the multiple correlation coefficient? How might it be useful? What's the eventual payoff going to be? Well, one, we will see it plays a vitally important role in model validation. So, right, when we learn more about building models, we'll talk about how to do something called validate your model. It's an important process. It's an important step. And we'll see that the multiple correlation coefficient plays a key role in this process. It also gives us a mechanism to compare models in which our y variable has been transformed. And so again, down the road, we'll talk about situations where instead of working with y, the weight of a bear, we might work with the logarithm of y, or maybe the square root of y. So now we have maybe y's on different scales, and it becomes hard to compare them. But one metric that we can end up using is we can compare the actual r's, the actual multiple correlation coefficients. We'll talk more about that maybe in this class. Definitely, I sometimes do a elective topics class in the application of statistical methods to business and finance, and in that category we use that third bullet point idea a lot. All right, so there we go. Right, what do we have? We had 4 things to talk about. Zero order correlation, check. The overall correlation coefficient, check. Next up, partial correlation coefficient. So the partial correlation coefficient measures the strength of the linear relationship between 2 variables after controlling for the effect of other variables. Probably most of us have an idea of what controlling means. It really just means kind of like what we talked about last class, right? This idea of, is there a relationship above and beyond what's also being provided by these kind of these other variables. We'll talk more about this idea of controlling a little later in the class when we get to like confounding. So if we're controlling for one variable, we call this first order partial correlation. If we're controlling for p variables, we call this the pth order. So you could have first order, second order, third order, 10th order. Just depends on how many variables you're controlling for. Here's the formula. It looks like a little bit crazy, right? So we denote this correlation coefficient. Here we're looking at the correlation between y and x controlling for some third variable z. So this is a first order partial correlation. There's the formula for that one. Formula gets a little bit crazier as you get to second and third and fourth order. And I mean, it's hard to kind of tease out like a very easy. I haven't found a way to break it down super intuitively. But I mean, one nice thing that we could see at least is like what happens if y and z are uncorrelated and x and z are uncorrelated. Right, that is essentially we're like saying the correlation between y and z controlling for something that's uncorrelated with them, which would mean there's sort of nothing to control for. In that case, we could see that like that second term in the numerator zeroes out. Those terms in the denominator zero out. And it turns out that formula simplifies, right, to just the correlation, the zero order correlation between y and x. So we can think of it as like an adjustment. We're adjusting that zero order correlation based upon the fact that one or maybe both of our variables might be correlated with some third variable. This is completely 100% analogous to partial f-tests. And let's go ahead and see that. So the partial f-statistic, which is used to test, at least in terms of how we described it last class, right? The partial f-statistic for a variable x is basically looking at whether the beta, the coefficient for that x is 0, not 0, in a model in which, right, all those z variables are present, is exactly equivalent to a hypothesis test for whether or not rho, the population partial correlation between y and x controlling for these other variables is equal to 0. Again, we have this nice preserved relationship that we've seen 2 other times up until now. So this is the 3rd instance of it. We can generate partial correlations using PROC-Core with the partial statement. So here, now what did I observe? We observed when we did the zero order correlations. When we did the zero order correlations, we observed that the sort of best variable was chest, right? So we said a type 1 approach to model building would be to put chest in first. The next step would be what? Of the remaining variables, length, neck, and age, which one adds the most above and beyond chest? This can be tested by looking at the partial correlations. So now we have this smaller grid of correlations. You can compare it. They're different than what they were in the previous slide because now we're controlling for chest girth. And you can see that way up on the top, right? Way up on the top it says one partial variable chest. That means that we're controlling for chest. So look at the column for weight. Of the remaining variables, neck seems to be the most strongly correlated. So the next variable we would add to our model would be neck girth. Notice length, which is highly correlated with weight by itself, is no longer correlated with weight after we take chest into account, as we sort of observed last class. So in terms of the type 1 process, what do? We add neck to our model. And then now we say, okay, of length and age, which one of these two variables adds the most above and beyond chest and neck? Yeah, so as we can see, we can use these partial correlations to implement a type 1 model building approach. Right, chest goes in first, and we actually just saw that neck would come in second. Yep, so we would add neck as the second variable to our model. Right, of all the remaining variables, length, neck, and age, we observed that neck had the highest first order partial correlation, right? That is after adjusting or controlling for chest. Right, so now we look at the correlation between of length with weight and age with weight after controlling for now these others. So now we're looking at a second order partial correlation. All right, and so of these, it looks like age is most strongly correlated. Right, its p-value is still below 0.05. So it adds a significant amount, so we would add age to our model. Next, that would be sort of the third best variable in our model. Yeah, so we add age, we run, we look at the correlation between weight and length. I'm expecting that to be a very weak correlation, but nonetheless, let's take a look. And we're now doing, what would that be? First, second, third order partial correlation? Yeah, and so we can see very weak, very weak, non-significant negative correlation after controlling for all these other variables. So because the p-value for this correlation is, right, 0.6426, we would not add it. We would not add it to our model. Of the 4 variables, chest, neck, age, and length, only chest, neck, and age appear to be useful in our model. Yeah, length doesn't add anything above and beyond chest, neck, and age, so we only need chest, neck, and age. Now remember, I said that this should be exactly the same as using PROC-REG. Right? The partial F-tests that we saw last class are equivalent to the tests of partial correlation. Same test statistics, same p-value. And so there it is, right? There's that p-value Little bit of deja vu. Look at the type 3 p-value for length in the parameter estimate, 0.6426. That's exactly what the p-value was for that third order partial correlation, because it's the exact same test. It's just two different ways of conceptualizing the same underlying idea. So in general, partial correlation gives us a nice way to discuss things like a type 1 model building process, right? We're adding the things that are most correlated with Y after accounting for any potential overlap with other variables that are already in the model. It's also useful in other statistical contexts. So another elective course that I often teach is time series analysis. And time series analysis, particularly building something called an ARIMA model, we use something called a partial autocorrelation. And a partial autocorrelation is just a partial correlation coefficient, like we're talking about right now. So they are used in other settings. All right. And then this one is largely here for completeness. I haven't really stumbled across any actual applied uses for this kind of multiple partial correlation. I'm not even really going to get too heavy into kind of reading all these bullet points on this slide. Again, just for completeness, I want to say that there does exist a correlation analog to the chunkwise F-test, and it turns out, right, that a test of whether or not this sort of chunkwise correlation is 0 is the exact same thing as that chunkwise F-test that we talked about last week. That again, they test the same thing, that there's this correlation analog. All right, pretty straightforward, right? Just kind of wrapping up loose ends. We've come a long way, right? I mean, this is week 5, but chapters 3 through 10, and you know, if you're someone who had to do a lot of reviewing, that's really chapters 1 through 10. So for our exam, we'll be taking it on D2L. You'll have you'll have the class period to take that exam. So you'll have whatever that is, a little less than 4 hours. I guess maybe like 3.5 hours. It is a closed book exam, closed resource exam. You can't Google anything. You can't search anything. You can't use your textbook. Can't pull up PowerPoints. Closed notes. No instant messaging with anybody. You can make yourself a note card. So if you want to make a little note card to help with some of these formulas, I know some of us are better than others at memorizing these formulas. You can make a note card of formulas. We will need tables, right? So I did tell you that we're going to be using tables. So however you want to do that, if you want to have your textbook handy, you can use it just for the tables in the appendix. Alternatively, I think there's some digital copies of the tables on D2L. If you want to just kind of pull those up on your monitor or computer screen, that's fine as well. And you'll definitely want a calculator. You will have to do some hand calculations. So make sure you have a calculator. Doesn't have to do anything too fancy. You'll just be, you know, adding, subtracting, multiplying, maybe squaring or square rooting some numbers. So again, some important topics, not necessarily comprehensive, but just to kind of remind you of kind of some of the things we've talked about. Right? We've talked about correlation in 2 different lectures. We talked about the ANOVA table. I would expect you to be able to kind of fill in that ANOVA table if some piece of information was missing from it, to be able to infer what that is based on the other pieces in the ANOVA table. I expect you to be able to interpret and perform hypothesis tests of slope and y-intercept. So again, it's not just doing the testing, but it's also the interpretation. How do we communicate what's going on, right, in a language that a non-statistician would find acceptable? You need to know the difference between type 1 and type 3 sums of squares, and of course that ties into the whole partial F testing that we talked about last class. You won't do any SAS code. I won't ask you to write any SAS code, but I certainly might give you some SAS output. So I might ask you, like, interpret something from the output. I might ask you, like, where does this number come from, right? In this output, there's a number 12. Reproduce that number 12. How is that 12 being generated from other parts of the output? Right? I expect you, this is maybe even going back to some of that review stuff. I expect you, any questions about hypothesis tests and confidence intervals, I certainly will ask some to try to discern how well I think you understand like these underlying concepts. So make sure you understand those well. You cannot be a good statistician if you don't understand hypothesis testing and confidence intervals. And I did not spend a lot of time teaching it other than the review. In the review, I did put some stuff, but even that was intended as a review. And it may be that you need more than that. And if that's the case, that's fine. I'll work with you. I'll help you. But you have to reach out to me and let me know that you need that work. You need to know, of course, the 4 assumptions. You can bet that's going to be on the exam. Right? You need to be able to write out these models, these theoretical models, these prediction models, write out the things with all the different betas in them. And of course, we talked about residuals in a different context, so that's something you should be aware of. All right, so there's a small lab. You want to make sure you do it, and then I'll have some extended office hours for any one-on-one time that you might want to kind of start wrapping up loose ends. So slightly smaller than normal lecture, with the intention that we use that extra time productively to catch up on any loose ends that we might have fallen behind upon in the previous weeks. And if you're in a fantastic position where you've been really doing a good job staying up on top of everything, then you get a little bit of extra time off for a little bit of time off for good behavior. All right, so study hard. That's what my old karate teacher used to say. He used to say, he said, practice hard, I guess. He'd always say, practice hard and go to church on Sunday. So I don't know that I'm allowed to tell you to go to church on Sunday. Truth be told, I don't go to church on Sunday. But I don't know. Study hard and do something fulfilling on Sunday. See you for the exam.